Hello viewers, I have discussed solid rock recrystallization at elevated pressure and temperature condition without change in the composition. We have discussed enough about the metamorphism. In this video, I will discuss types of metamorphism. This video is in two parts. I will take up first part here in this video. The solid rock crystallization produced by rise in temperature and pressure at great depth is called metamorphism. This is the definition of metamorphism. In this metamorphism, no significant change in bulk composition except alteration that takes place. In this video, we will discuss various types of metamorphism. Metamorphic process is liable to mineralogical, structural, chemical changes in solid rocks initiated by temperature and pressure changes, shearing stress, and chemical fluids charged with gases. Metamorphism is the process that brings about changes in the mineralogical and or structural and or chemical constituents in a rock, dominantly solid. Metamorphism is regarded as a thermal phenomena in which heat is the most important source of energy, causing mineralogical and textural reconstruction. Metamorphism coexists with partial melting and may involve recessive changes in bulk chemical composition of the rock. The term metamorphism is applied if changes in bulk composition is the dominant metamorphic process. Here, there are types of metamorphism. Metamorphic rocks derived from various processes is called metamorphic rocks, but there are different types of metamorphism. The terms used to classify metamorphism are thermal metamorphism, where the heat plays very significant role, that plays the dominant role, whereas dynamic metamorphism, where deformation and recrystallization takes place. In case of dynamothermal metamorphism, both temperature and stress that plays very significant role. The traditional classification is based on geological setting, that is regional metamorphism. Geological processes acted over widespread areas, covers linear belts, causes metamorphic changes in rocks of vast areas. Local metamorphism due to local metamorphic effects in a restricted area occurs due to magmatic intrusion, faulting or meteoritic impact. Metamorphism classified based on their extent. Regional metamorphism is on my left hand side, whereas local metamorphism, which is local in extent, is on my right hand side. The regional metamorphism is mostly connected with the orogenic belts. Ocean floor metamorphism, then subduction metamorphism, collision metamorphism, and burial metamorphism. They are all classified under the regional metamorphism and they are regional in extent. Local extent, in this case we have contact body is igneous rock and the rock surrounding that igneous rock produces metamorphism, which is called contact metamorphism. Cataclastic metamorphism, impact metamorphism, hydrothermal metamorphism, lightning metamorphism, combustion metamorphism. Now let us take up one by one the regional metamorphism. Miyashiro 1973 suggested term orogenic metamorphism, which is a regional metamorphism or dynamothermal metamorphism. Significantly, it affects rocks on regional scale and covers mountain belts. It involves temperature and pressure changes and deformation and recrystallization. It is caused by orogenic processes attended by recrystallization and deformation. The regional metamorphism linked to large-scale tectonic processes such as ocean floor spreading, crustal thickening related to collision of plates, subduction, deep basin subsidence. The diagnostic features are penetrative fabric or mega and microscopic scale and preferred orientation of grains in phyllites, schist and gneisses, temporarily long lasting for millions or tens of years. The ocean floor metamorphism, Miyashiro 1973 discussed that changes occur in mid-oceanic ridges. The special extent is large ocean floor spread by lateral sea floor, rocks mainly non-schistose, basic, ultrabasic, peridotites and basalts. The temperature gradients several hundred degrees centigrade akin to continental burial metamorphism. Diagnostic feature extensive veins and metamorphism due to convection of vast amount of heated seawater. Convective circulation leads to chemical interaction between rocks and seawater, which marks the resemblance of ocean floor metamorphism to hydrothermal metamorphism. Here is the mechanism. Rise of crystal water in vicinity of volcanic heat source causes drying in water, more water rather, that creates convective currents. Cold seawater drawn into the crust and heated to 200 degree to 300 degrees centigrade then passes through crust and again released into sea floor near ridge. Rocks versus seawater chemical interaction, which is similar to ocean floor metamorphism to hydrothermal metamorphism. Here is the diagram which shows ocean floor metamorphism of oceanic crustal rock on either side of a spreading ridge. Here we have a ridge in the center and both sides we have a circulating seawater that goes down into the deeper level and comes up to the shallower zone, and this is a heated water. Heat is heated up to 300 to 400 degrees centigrade. The subduction zone metamorphism, orogenic metamorphism is of two types: subduction zone metamorphism, collision zone metamorphism. Subduction zone metamorphism takes place under the very high pressure and relatively low temperature conditions. The mechanism is oceanic lithosphere is pulled down into hot mantle in subduction zone, slab subducts deeper into the mantle and high pressure is developed. Rise in lithostatic pressure due to increase in collisional force between tectonic plates. Subduction zone metamorphism takes place under very high pressure but fairly under low temperature conditions. Example is Indus suture zone in Ladakh, Himalaya. Here is the diagram. Subduction zone showing metamorphism of oceanic crust at subduction zone occurs at high pressure but relatively low temperatures. The collision zone metamorphism, continental crust along convergent tectonic margins of continental plates or collisional plates produces folded, broken, squeezed and stacked rocks. Deeper rocks in stack suffer high grade of metamorphism due to high pressure and temperature. Both subduction and collision zone orogenic metamorphism are related to major intervals of a Wilson cycle of orogeny. It includes several distinct episodes of crystallization and deformation. Regionally metamorphosed rocks show grain size increase and textural changes with rise in metamorphism. Each deformation phase represents distinct attitude and schistosity direction, folding and lineation. Several deformation phases visible in the field and possibly grouped into time sequence. Structural features linked to mineral growth visible in textures under the microscope and helps to establish deformation and metamorphism relations. Here is again a diagram figure which shows increasing intensity of metamorphism from low grade, intermediate grade to high grade metamorphic rocks. The increasing crystal size is also shown here, and the regional metamorphism changes rock texture from slaty cleavage, low grade phyllite, intermediate schist, abundant micaceous minerals are there, gneiss, fewer micaceous minerals which shows banding, and high grade migmatites which also shows banding. Here is another example of foliated metamorphic rocks. Slate, for example, compact, very fine grained metamorphic rock with well developed cleavage. Freshly cleaved surfaces are dull as shown in my right hand side, whereas the phyllite possess schistosity in which very fine phyllosilicates impart silky sheen to foliated surface. Phyllites with both foliation and lineation are very common, as shown in my left hand side. The foliated metamorphic rocks, schist, metamorphic rock exhibiting schistosity. In common usage, schists are restricted to those metamorphic rocks in which foliated minerals are coarse enough to be seen easily in hand specimen. Here is the garnet muscovite schist. Muscovite crystals are visible and slivary. Garnet occurs as large dark porphyroblast. The another example is foliated metamorphic rocks, which shows garnet mica schist showing microfolding. The foliated metamorphic rocks, the example is gneisses, metamorphic rock displaying gneiss structure. Gneisses are typically layered with alternating felsic and darker mineral layers. Gneisses may also lineated, but also must show segregations of felsic and mafic mineral rich concentrations. Here is the example of quartzo-feldspathic gneiss. Burial metamorphism. Another kind of metamorphism is burial metamorphism. It occurs at the bottom of the thick sedimentary sequence. Depth range is 6 to 10 kilometers. Temperature range 100 degrees centigrade to 200 degrees centigrade and depends on geothermal gradient. Coombs 1959 defined burial metamorphism for interlayered volcanic rocks in a geosyncline where sediments affected by low temperature regional metamorphism. Deeply buried sediments suffer high temperature and pressure. As a result, new minerals crystallize and grow. Rocks affected by burial metamorphism does not show foliated appearance. Burial metamorphic rocks develop less or no foliation, occurs at relatively low temperature up to 300 degrees centigrade and pressure of 100 meter depth. Diagnostic feature: original fabric preserved that lacks in the schistosity. New found mineral assemblage is closely associated with mineral grains left from the original rock. As mineralogical changes are usually incomplete, there is intense similarity between deep-seated diagenesis and burial metamorphism, which cannot be distinguished. For example, southern New Zealand and Chile. Deeply buried sediments undergo burial metamorphism due to growth, the heat and pressure. Summary. Here is the summary of the entire video. Types of metamorphism: A. Regional metamorphism and B. Local regional metamorphism includes geological processes acted over widespread areas and cause metamorphic changes at the expense of huge amount of rocks and includes ocean floor metamorphism, subduction metamorphism, collision metamorphism and burial metamorphism. Local types of metamorphism will be discussed in the next video. Thank you, viewers.